All right. So last time, what we did is we covered volume using the shell method. And with the shell method, the idea is that we take our Riemann sum rectangles and we revolve those. If we revolve those parallel, if the rectangles are parallel to the line I'm revolving around, then I've created a shell, nested shells. But those nested shells, when I take the sum and I let the thickness go to 0, limit as the thickness goes to 0, I'm going to end up with the actual value. So the last couple of sections, both 7.2 and 7.3, we've been dealing with value. So we're going to switch that up. And in 7.4, we're going to deal with arc length and surface area. Now, basically, the question is how, let's start with arc length. How would I find the length of a smooth curve? So I have a smooth curve. What's going to happen is I'm going to use the distance formula. And the distance formula is just like the Pythagorean theorem with right triangles. The distance is a squared plus b squared underneath a square root. Okay? That's of a straight line. So straight line distance from point 1 to point 2 I would find the distance between point 1 and point 2 by using essentially the Pythagorean theorem, right? That's what I'm saying, if we have a straight line. So what would I do if I had a smooth curve that's obviously not straight? Well, what I'm going to do is I'm going to approximate distances by points on the straight line. And so I'm going to ask myself, well, what's the straight line distance between these 2 points? And then what's the straight line distance between those 2 points? And what's the straight line distance between those 2 points? And those 2, and those 2, and those 2, and those 2, and so on and so forth. I'll get all of those little distances and add them up. And then, if I want an even better approximation, I just add more points. And each of these little pieces mimics the curve fairly closely. And so if I take each one of these little distances and those distances I'm going to calculate with a straight line, which I know how to do, then I'll add those up. And so to find arc length, we're just going to keep that process and keep adding more and more points by letting the distance between point 1 and point 2 get smaller and smaller and smaller and smaller. So in other words, the limit between the points goes to 0, and we're adding a bunch of straight line distances. And that, as the limit goes to 0 and the sum goes to infinity, is going to turn into the arc length. All right. So if we have a curved line or just a smooth curve, we're going to approximate it with straight pieces. And we're going to add up all those little straight pieces. And then as I get more and more and more pieces, I'm going to get closer and closer to the arc length. So if I take the limit, as I get more and more and more pieces, it's going to give me the arc length. And this sum, obviously we're going to add up more and more and more pieces as well. And if you use x values, then the arc length is the integration from a to b, x value of a to x value of b, in the square root of 1 plus f prime of x squared. By the way, arc length usually is denoted by a lowercase s. And obviously, if we use x's, we'll use values a's and b's just like we did before. If we use y's, we'll use c's and d's, just like we did before as our bounds. Let me show you where the derivative comes out of. Okay? Where the derivative comes out of. Now, in order to do this, I'm going to do a slight rewrite of my distance formula. Here, we said the distance formula is a squared plus b squared. What is a? Well, a is simply how much change there was in the x values. So change in the x values is delta x. B is how much change there was in the y values. That's just delta y. You guys know that delta notation just means change in x, change in y. Triangle. It's the Greek letter delta. Now, what we're going to do is the following. My distance formula is going to be rewritten this way. I'm going to essentially factor out delta x squared from both this term and from this term. If I factor it out from this term, this is just delta x squared, so I get a 1. When I factor it out of this term, I get, well, it's delta y divided by delta x, and I'm going to square the delta y, and I'm going to square the delta x. So I'm just going to write this whole thing squared. Is that right? Now, the reason I'm doing that is so that I can take a square root of this delta x squared, and I can't do that unless it's being multiplied. So I'll take a square root of change in x squared, which is just change in x. And what's left underneath my square root is this part, 1 plus delta y over delta x squared. So that's the distance formula, written in a different way. Now, the nice thing about that way that the distance formula is rewritten is that we can easily see now where our surface area comes from. As I let change in x go to 0, limit as this little piece goes to 0, and then I sum up all of those. Well, as change in x go to 0, this delta x changes into my dx. And change in y over change in x, the limit of that as your change in x goes to 0 is simply the slope of your tangent line, which is the derivative of my f prime, or the derivative of f, or f prime. Okay, that's exactly what the derivative is. So, noticing this is just a rewrite of the distance formula kind of tells you where the arc length comes from, that arc length formula comes from. Okay. Now, that's where the arc length formula comes from. Once we know these arc length formulas, or once we have these written down, then we can simply just apply those to some curve over some interval. So let's say we want to find the arc length of the curve y equals x to the third plus x plus 1. On the interval from 2 to 5. By the way, when I say closed interval from 2 to 5, that's always going to be in terms of x values, okay? So that says from x equals 2 to x equals 5. So let's set up my arc length formula. It's pretty straightforward that if our bounds are from 2 to 5, then I'm going to be integrating from 2 to 5. I'm going to take a square root of 1 plus the derivative of my function. Now, my function is x to the third plus x plus 1. So if I call that my function, then the derivative of that function is simply 3x squared plus 1. Does that make sense? That's my function written with respect to x, like y equals a function of x. So 3x squared plus 1 is the thing I need to put in here for the f prime. Be careful of that. Some people will get in a hurry and put in the original function instead of the derivative of the original function. We need to put in the derivative. Now, technically, we could do this by hand, but it's quite a mess to try to do by hand. So instead of doing this by hand, we're going to reach to our calculators just like we've been doing the last few days. And I'm going to plug that into my calculator. Be very careful that you have all the pieces. Especially dealing with the square root and what's underneath the square root. We have 1 plus this whole piece is squared, but it's all underneath the square root. Okay. And I got approximately 120.05. So the arc length of that curve is approximately 120.05. If you think about what that means in terms of the graph, this one's pretty steep. So might not be a great example, but I'll still go to Desmos. Y equals x to the third plus x plus 1. Let's do from 2 to 5. So what we're talking about is the curve y equals x to the third plus x plus 1 from 2 to 5. And that gets huge real quick. But we're talking about the length of this thing. Oh, I'm sorry. I thought that was on. Sorry. My bad. So the length of this curve from here to here. And I can't just do a straight line from this point to this point. So from 211 to 5,131, because it's not a perfectly straight line. By the way, if it was a perfectly straight line from 211 to 5,131, notice it would have been exactly 120 units. Or not quite exactly, right? Let me say that again. Yeah, 211 to 5,131. You could have, figured out the length of that exactly if it were a straight line. But because there's a little bit of curve in it, it turns out the length is about 120.05. Does that make sense? So there's just a little bit of curve in that. I want you to try this one. Find the arc length of the curve y equals sine x from 0 to pi. Make sure your mode is in radians. We're always in radians unless otherwise stated so. Y equals sine x, 0 to pi. All right, so the setup, you can done. Let me rephrase this. So because I already have y is equal to a function of x, I'm going to use this type of arc length, right? We already have y is equal to a function of x. So we're going to use the f of x arc length. We're going to integrate with respect to x. And that means when I have y equals sine x, I take the derivative to get y prime as cosine of x. So cosine of x is going in here. It's going to get squared. Then we're going to add 1. Then we're going to take the square root of that. And then we're going to integrate from 0 to pi. So we integrate from 0 to pi, square root of 1 plus cosine squared. And I end up getting approximately 3.82. Again, this integration, you might be able to do it by hand, but it's much, much easier to just throw it in the calculator. Any questions about that arc length? How to set that up? Pretty straightforward. All right. The next one I'm actually going to do 2 different ways. Okay? We want to find the arc length of this curve. Y minus 1 cubed equals x squared. from x equals 0 to x equals 8. Now, one thing you'll notice about this particular curve is that it's not solved for y. We don't have y equals. And it's also not solved for x. We don't have x equals. So let's take a look at Desmos of what that thing looks like. Y minus 1 cubed equals x squared. Looks like that. Okay. Looks like this almost V-shaped, but it's obviously curved. And then we're going to go from x equals 0 to 8. So we're talking about that section of that V. All right. Everybody okay with that? So this little section. So I want to find the length of this. Now, since it says from x equals 0 to x equals 8, I'm going to start off doing this problem like we did before, integrating with respect to x. That takes a little bit of side work on this example. So y minus 1 cubed equals x squared. If I'm integrating with respect to x, I need to get y equals a function of x. So that would mean I take y minus 1 is equal to x to the 2/3 power. If I take 1/3 power to each side, does that make sense? Take 1/3 power to each side, and then add 1 to each side. I get y equals x to the 2/3 power plus 1. Now, that's just solving for y. I don't need my function in here. I need the derivative of my function. So when I take and find y prime, 2/3 x to the negative 1/3 plus 0. Right? You take the exponent, put it out front, and then lower your exponent by 1. If I take 2/3 and lower it by 1, I get negative 1/3. So my arc length should be the integration, again, I'm doing this with respect to x, from 0 to 8 of the square root of 1 plus 2/3 x to the negative 1/3 squared. That ends my square root. Integrated, obviously, with respect to x. I'm just going to type this into my calculator. Be very careful on parentheses and all of that kind of stuff, because this has a lot going on, so it's easy to mess up the typing of it in. And because we're integrating, and because I have a negative exponents and all fractions of exponents, it's going to take a minute to actually compute what this integration is going to be. All right. I got an arc length of approximately 9.07. All right. Again, it's very important that you type things in a very, very precise way. Now, that's the option where I integrate with respect to x. It turns out in this case, I could have also just as easily integrated with respect to y. Now, I do have to be careful when I integrate with respect to y. On a number of things. The first thing I have to be careful of is how do I find the g of y and then the derivative of g of y? Well, what I would have to do is solve for x in this equation. Now, we just saw the curve that I was talking about, right, on Desmos. We projected that up on the board. And you notice that from x equals 0 to x equals 8, we were in the first quadrant. That means if I want to solve this for x, since my curve is in the first quadrant, I know I can take the positive square root. Does that make sense? Or if I wanted to rewrite that, I could take both sides to the 1/2 power. So a square root of something cubed is the same thing as that something to the 3/2 power. It's going to be easier to take my derivative if I have 3/2 power than a square root. So now I've solved this for x. Now I'm going to take a derivative, not with respect to x, but with rather respect to y. Since I'm using y's, I got to take the derivative with respect to y. So I would take the 3/2 out front. Y minus 1, lower the exponent by 1. 3/2 minus 1 is a positive 1/2. And then the chain rule would say multiply by the derivative of the inside function. But the derivative of the inside function is just 1. So multiplying by 1 doesn't change anything. So my arc length is going to integrate a square root of 1 plus 3/2 y minus 1 to the 1/2 power, all squared. Again, integrated with respect to y. Now, here's something else you have to watch out for if you're integrating with respect to y. The integration is not going to be from 0 to 8 anymore. Not going to be from 0 to 8. The x values were from 0 to 8. If I go back to this one, when x is equal to 0, y is equal to 1. Just plug in a 0 into that, you get y equals 1. And when x is equal to 8, y is equal to 5. Again, just plug it in, see that you get what you get. And so integrating from x values of 0 to 8 is integrating from y values of 1 to 5. Does that make sense? Now, this gives me, rounded to 2 decimal places, the exact same value, 9.07. Rounded to 2 decimal places, the same value. But I do want to show you oh. All right. Excuse me. There we go. That's I do want to show you that on my calculator. So I've typed both of these in, right? Both the integration with respect to x version and the integration with respect to y. And I used alpha y here just so you saw the difference, okay? So I was trying to be careful. I want you to notice that these two are the same out to about 5 decimal places. But then once you get to the 6th decimal place, it changes a little bit. And that's because of the way the calculator is integrating. The calculator is integrating, it takes approximates over and over and over. And so sometimes when we're dealing with square roots and when we're dealing with negative exponents, especially around where x is 0, or where our inputs are going to be end up as 0 underneath the square root or 0 inside of a negative exponent, that can throw off the calculator by just a little bit. So obviously it doesn't make a difference if we round to 2 decimal places, but if somebody were to say, well, let's round this to 9 decimal places, you might get a slightly different answer. Okay. By the one I guess is probably more accurate to the real thing is probably the second one. Because this negative exponent in the first one might be, throwing things off at a microscopic level. That makes sense. So again, just to reiterate, if you are going to integrate with respect to y, then what we need to do is we need to create a function where the variable is y, and I think of the output as being x. Take a derivative with respect to y on that function, and then plug it in. And make sure your bounds, if you're integrating with respect to y, are y values rather than x values. All right. That's enough of that. So we found arc length. Arc length is a pretty straightforward formula, square root of 1 plus f prime squared integrated from a to b with respect to x. Or with respect to y, you just change the f of x to g of y. Well, what we're going to do is we're going to take a curve like the ones we just dealt with. And just like we did with value, we're going to rotate those around either a horizontal or a vertical axis. So we're going to rotate or revolve the curve around some axis. Now, if you think about what that does, revolving a curve around a horizontal or a vertical line it's going to create kind of a shell. Think about an empty eggshell. All right. And our goal is going to be to find the surface area of that empty eggshell. So I take a curve, revolve it around some line. Let's say for my demonstration, I take that curve and I revolve it around the x-axis. So I get kind of a ghost image of that. Now notice again, this is not solid. So when you do this, you just get the shell, basically. And we're asking, what's the surface area of that thing? And so what we're going to do, just like before, we're going to take little pieces, little sections just like we did with the arc length, and I'm going to rotate those around. If I rotate that around here, what I've done is I've created basically a little shell or a little disc piece, right? A little cross section of the disc. There's nothing inside this disc, all right? This is just the shell piece, just the outside edge. Okay, so think of it like a paper right? I've created something like this, right? Something like this. And I want to find the surface area of this thing. Obviously, I should have used a smaller piece of paper, but that's okay. right? Let's find the surface area of this thing. Okay. And so what I do is I say, well, what if this thing, these little sections here are going to be based by the arc length, right? The size of these things, those are going to come from the arc length. And then I rotate that arc length around. And you think of, well, what is the circumference here? Well, whatever the radius is, the distance around is the circumference of the circle, which is 2 pi times the radius. So when we go to find surface area, it's going to be 2 pi times the radius. And then I have to multiply by whatever the length of this arc length is. So it's going to be 2 pi radius times arc length. And then obviously arc length here, formula is going to get changed into some other stuff. So let me just project out the actual formula. We're going to take a bunch of sums as the thickness of those little sections go to 0. And my surface area formula is either going to look like 2 pi integrate radius function times the arc length piece of square root of 1 plus f prime squared with respect to x. Or if I'm doing things with respect to y, it's still radius, but our radius is with respect to y. Square root of 1 plus g prime of y squared integrated with respect to y. So it's basically like an arc length formula where I've multiplied by 2 pi times radius. And since the radius is going to vary depending on where I'm at on the function, my radius is going to be a function of x or a function of y. So basically, arc length formula times circumference, where radius is going to be from the curve down to the line I'm rotating around. Does that make sense? Radius is from the curve to the line I'm rotating around. As seen in the picture I just erased on the board. So let's try to do this. let's find surface area. Formed by revolving y equals x to the third plus 2x plus 1 around the x-axis on the interval from 0 to 4, closed interval from 0 to 4. All right. So we have this y equals x to the third plus 2x plus 1 from 0 to 4. And if you actually calculate the points, that means it starts at the point 0, 1 and ends at the point 473. Okay. So we're taking that section and we're going to revolve that around the x-axis. So revolve it around the x-axis. If you take a little section and we go from the curve down to the x-axis, let's say we want to, well, obviously we want to integrate with respect to x, right? Because I don't want to solve this, try to get x equals function with respect to y. So I want to find my surface area by using 2 pi, integrate from a to b, radius with respect to x, square root 1 plus f prime squared with respect to x. This is pretty straightforward. If we're integrating with respect to x's, I go from x value of 0 to x value of 4. My radius is going to go from the curve down to the line I'm rotating it around. The curve is x to the third plus 2x plus 1 down to 0. Now, in order to throw things underneath the square root, I need to take the arc length of the curve that I'm dealing with, put that in the square root, which requires me to take a derivative with respect to x. And similar to the one we did before, that derivative of the curve is 3x squared plus 2. So that goes in for my f prime x. Be careful when you type this in, because a lot of people, if they forget these parentheses, throw their answer off. Because this entire r of x needs to be multiplied times the entire square root. So make sure you include those parentheses when you type it into the calculator. There's a lot of times people just type in the wrong thing, basically. And so the answer to this problem is approximately 16,750.70. That what you got? 16,750.70. Approximate. That's a rounded to 2 decimal places answer. So just be careful about how you type that in. There's a lot of stuff going on in the integration. You can imagine how hard of a problem this would be if you tried to do this by hand. It'd be a very, very difficult problem if you had to try to do that integration by hand. So that's why in this class, we just round to 2 decimal places. We say, here's the setup, round to 2 decimal places, and then we're good to go. So we're going to take the same surface area, not the same surface area, excuse me. We're going to take the same curve. And instead of revolving around the x-axis, we're going to revolve around the line y equals -5. That's going to make that shell bigger, and therefore the surface area is going to get larger. So we're going to take that same curve, that same chunk of curve, rotate it around y equals -5, and find the surface area of the object we've created. Now, once again, I still want to be integrating with respect to x, because I don't want to have to solve this for y or do anything like that. In this case, y equals -5 is a horizontal line down there, right? Below the x-axis. How does that change my problem? Well, it turns out not very much. I'm still dealing with the exact same curve. So when I'm thinking about my f of x and my f prime of x, my f prime is still 3x squared plus 2. That part doesn't change. Everybody understand why? The reason this part doesn't change is because this part comes from the length of the curve. It doesn't care about where it's rotated around. This part doesn't care about that. This part is the part that's going to change, the radius. And how it changes in this case, my radius starts at this curve, y equals x to the third plus 2x plus 1, and it goes all the way down to y equals -5. So my radius is going to be x to the third plus 2x plus 1 down to a -5. That's like adding 5. Are you okay with that? Subtracting a -5 is the same thing as adding 5. The A and B are still bounds on our curve, so it's still going to go from 0 to 4. So if I rotate around another horizontal line, really the only thing that's changing is the radius. Now, obviously, changing the radius is going to change my final answer. In this case, it changed it to 19,021.21. That makes sense? Okay with that? So anytime we're revolving around a horizontal line, curve to down there. By the way, this radius, when we're revolving around a horizontal line and integrating with respect to x, this radius is just like the radius from the disk method. Does that make sense? So if we're revolving around a horizontal line, I go from curve down to line I'm revolving around. Again, just like this radius is just like the disk method radius when we're dealing with integrating with respect to x and revolving around horizontal lines. All right, let's do another example. So my next example is this. We're going to revolve y equals x squared plus 2. Around the y-axis on the closed interval from 0 to 4. That means from x equals 0 to x equals 4. So if we draw the picture, y equals x squared plus 2 is a parabola from 0 to 4. I'm going from the point 0, 2 to the point 4, 18. That's my curve, right? Maybe I should have drawn that in black, but that's highlight it. And I'm revolving around the y-axis. Now, each one of the little sections is going to be a little section of arc length. And then I'm going to be revolving around the y-axis. So my radius is going to go from here to here. This one can actually be done in a couple of different ways. Let's say I look at this and I say, you know what? We have a vertical line that I'm rotating around. And in the previous two problems, I've used a horizontal line. And I've integrated with respect to x. So let's integrate with respect to y, since we're using a vertical line. In this example, that's okay to do, because I can take y equals x squared plus 2 and solve that for x. Fairly easily. When I solve y equals x squared plus 2 for x, I get x equals y minus 2 to the 1/2 power, or square root of y minus 2. I can do that because the section of curve that I'm dealing with is all in the first quadrant. So I can take the positive square root, right? Or I can take the positive version of y minus 2 to the 1/2 power. Now, before I move on, I'm going to take a derivative of that, because that's going to be my curve, and the g prime with respect to y is going to be the derivative of x equals y minus 2 to the 1/2 power with respect to y. So take 1/2 power, y minus 2. If I subtract 1 from a half, 1/2 minus 1 is negative 1/2. And then I would multiply by the derivative of the inside function. Since the derivative of the inside function is 1, I don't have to deal with that. Okay. Any questions about that so far? All right. So if I want to find surface area where I integrate with respect to y, my bounds my lower y bound is 2. My upper y bound is 18. My radius goes from this curve, this one, down to the line I'm rotating it around, which is simply x equals 0, right? The y-axis. So it's from this curve, from y minus 2 to the 1/2 power, down to 0. And then the arc length part is going to be square root of 1 plus the derivative of the curve squared. Now the derivative of the curve, once again, is 1/2 times y minus 2 to the negative 1/2. And we're squaring all of that. I know it's a lot to type into the calculator, but it's not terrible. There are worse things. So let's type that into the calculator. Oh, I think I misspoke. Either I misspoke or I miswrote and I spoke correctly. I can't remember what I said. Y value should go from 2 to 18, right? 2 is the y value. The lowest y value of the curve. 18 is the highest y value of the curve. I don't know which one I did. If I said 2 to 18 and then wrote 0, both are on me. Again, it's going to take a minute. But that being said, I get approximately 273.87 as the surface area of this. Okay. Now, let's do this the other way. We're going to set this up and do the exact same problem, or find the exact same surface area using a different method. This time, let's say we want to actually integrate with respect to x. So I'm doing the exact same problem, but now I'm going to be integrating with respect to x. Now, because I'm integrating with respect to x, y is already written as equal to a function with respect to x. So I can simply take the derivative as 2x and plug it in here. All right. Now I'll get there in a second. The x bounds go from a to b, and for the x values, that goes from 0 to 4. 0 to 4 for x values. Pretty obvious. Now here's the trick. So the f prime is a lot easier to deal with. It's just 2x. The bounds are nice to deal with. They just go from 0 to 4. The radius we have to think through. What is the radius in this case? Well, the radius goes from some x value down to an x value of 0. So what I'm saying is, well, the radius depends on where I'm at on the curve, right? So just like the shell method radius, it goes from arbitrary x value down to 0 if I'm lengthened that way. Does that make sense? So my radius in this case is like the shell method radius. This is the way I prefer to integrate. I prefer not having to solve for y like we did earlier. Like solve for x, get x equals a function of y. I prefer to say, well, anytime I'm revolving around a horizontal axis, then the radius with respect to x is like the radius of the disk method. And anytime I'm revolving around a vertical axis, like this example, then the radius is like the radius of the shell method. I'll write that down in just a moment, but for now, I want you to realize that this is also much easier to type into your calculator, this version, than was the one we dealt with y's. So 2 pi integrate from 0 to 4. And we just got x minus 0 times the square root of 1 plus 2x quantity squared. And sure enough, I got the same answer of 273.87. Approximate. I should say it's the same answer out to all the decimals that my calculator gave me. Might not be the same. Hopefully that you see that that's a much easier integration to deal with. In fact, this one is not that bad to do by hand. If you had to do this by hand, you could probably accomplish that. All right, it's just a standard substitution. And then goes through. This other one by hand would be a nightmare. Okay? The one we just did, if we had to do that by hand, that would be much, much more difficult to deal with. All right? So this is kind of the disk method radius versus the shell method radius. And just so that I write this down, if integrating surface area using, I should have said it's defining surface area, sorry. I'll just leave it that way, even though it's poorly written there. Integrating, finding surface area using integration with respect to what? With respect to x. Then horizontal axis of revolution means the radius r of x is like the radius in the disk method. Vertical axis of revolution means r of x is like the radius in the shell method. Okay. By the way, if you integrated with respect to y, it'd be the exact opposite. It'd be the reverse. Right? Horizontal would be like the disk method. Or excuse me, horizontal would be like the shell method. Vertical would be like the disk. You integrated with respect to y. But most people like to integrate with respect to x, just so they don't have to resolve and solve an equation. Most times, when given a problem, people think of y is equal to a function of x. We use x as our variable. This all right? Making sense? Either way, we get the same answer, but one way is just shorter than the other. And in this case, integrating with respect to x was the shorter method, was the quicker method in this example 6. Now, either way gives you the same answer, but as always, in this example, I could solve and get x equals a function of y. There are some equations in which I can't solve for x. Right? And so having an understanding about how to integrate use with surface area is very important in those examples. Let's do another example of finding surface area. I want you to try this on your own and integrate with respect to x. We've just dealt with this same curve. So most of it should be pretty straightforward. All right, so let me go through this. I'm gonna integrate with respect to x. And if I do that, then I'm gonna have to deal with this y equals x squared plus 2 as my curve. And I'm gonna revolve it around a vertical line, x equals 6. So each of my little pieces that I get with my surface area, I'm gonna revolve around that line. Get this shell. So we have to do a couple of different things. One thing is I have to take the derivative of the function that generates this curve. That is, the function is y equals x squared plus 2. So the derivative is y prime equals 2x. Since I'm going to integrate with respect to x, my curve goes from x value of 0 to x value of 4. I am revolving around a vertical line. That means I'm going to go from an arbitrary x value, wherever that happens to be between 0 and 4, around my line that I'm rotating, which is x equals 6. Now, if I write x minus 6, I'm actually going to get negative numbers because all of my x values are below 6. So I'll get a negative surface area, which doesn't make sense. So in order to get a positive surface area, I start at the 6 and I go down to the arbitrary x value. Derivative of my function, again, is 2x. And I'm going to be integrating with respect to x. Again, if you would have accidentally put x minus 6 here instead of 6 minus x, you'd have gotten a negative surface area of what I get. But again, x equals 6 is bigger than all the x values that I'm dealing with. So that's it. When I plugged that in, I got approximately 360.18. Okay. And by the way, I haven't been mentioning units yet. I haven't talked anything about units, but hopefully we know that if we're talking about an area, it's whatever units that I'm dealing with squared, right? All areas are square units. Value, when in 7.2 and 7.3, we calculated value using the disk method and the shell method. That would have been in cubic units or units cubed, whatever units we have. In 7.1, we were talking about area, so it would have been in square units as well. Now, just to, again, sort of visualize what we're doing, we're getting this sort of big tube, right? We're getting some sort of a big tube, like an empty cylinder. And then we're saying, well, if you flatten that tube out, what would the area of the sheet be if you flattened it out? Now, this is a straight cylinder. What I'm holding, the piece of paper, is a straight cylinder. This would not be. So if you were to flatten it out, you'd have to flatten it out and cut it in certain ways and it'd be really hard to flatten out. But the point is the area, the surface area of that object is going to be 360.18. All right. So the area of the surface of that object is 360.18. Oh. I want you to try this example on your own. This will be the last example we do. In this section. Well, I shouldn't say that. I'm sorry. Last example we do today for this section. Silence. Round y equals 3. Interval. All right, so let's take a look at this one. We have our sine curve from 0 to pi, so only this section of the sine curve. And we're rotating that around y equals 3. So it's a line up here. Let's draw just a representative little section for my Riemann sum on the surface area. Now, I generally always like to integrate with respect to x if I already have y equals a function of x. That's especially true in this case, because if I had to solve and get x equals something, I would have ended up with x equals arc sine of y, and then I would have had to take the derivative of the arc sine of y, which is something that I don't have memorized. Does that make sense? So that would have been really, really tricky to do. Being what it is, taking a derivative of sine is something we've done a lot of. Derivative of sine is cosine. So it's a much, much easier derivative to take if we just leave it as y equals sine x. All right, so now I think we can start. My bounds are going from x value of 0 to x value of pi. My radius, well, it's going to go from the curve to 3. Notice that 3 is the bigger piece. And because this is a horizontal line, when I say it goes from 3 to the curve is going to be represented by sine of x. So it's going to go from 3 down to sine of x. If you do sine of x minus 3, you just get the opposite of the surface area that we were looking for. So that's the radius. The derivative of my curve is cosine. So I'm going to take cosine of x squared plus 1 all underneath that square root. And that's the setup. When I typed that into my calculator, I got approximately 57.59. It's 585 or something like that. Is that all right? So this one, since we were revolving around a horizontal line, we used the radius that was like the disk method radius. From the line, y equals 3, down to the curve that I'm rotating. Y equals sine of x. In our last problem, we revolved around a vertical line, and we used the radius like we would in the shell method. Arbitrary x value out to 6, or 6 down to an arbitrary x value. Does this all make sense? All right. Well, now you have all of the tools you need to integrate and deal with both arc length and surface area. Okay. Most of the time, it's going to be easier to integrate surface area using the variable x, as long as we're able to go back and forth between the radius like we would in the disk method, or the radius like we would in the shell method, like we had in the disk method, or like the radius we had in the shell method. Any questions about surface area? Now, I will do another example, next time. It's not on the slides, but, I'll do an interesting example of volume and surface area. Okay? Is a weird concept next time, okay? All right, well, we will end here. Remember, there's homework due on Friday. This surface area, arc length section from 7.4 is due on Friday, along with 7.3. That's the shell method. Other than that, I'll see you next week, Tuesday.